I'd like to have the first slide. So I thought that as an observer or experimentalist, I should try to give you a very practical talk about cosmology. And I think the idea I was hoping to play on here is that most of what we've been discussing so far feels like it's a very abstract and mind-boggling, which it is. But what is amazing to me is that we actually get to ask some of these very abstract, mind-boggling questions in very simple, practical ways, and I don't want to lose track of that. So I want to tell you a story about how we measure that the universe is not only expanding, but the expansion is speeding up. And tell it in just the simplest language so that you'll all have this very concrete sense that we actually live in this mind-boggling world. So I'm going to begin with the question that I've always imagined that the very first human beings must have asked as they walked outside of their caves at night and looked up at the stars and found themselves wondering, does this go on forever, and does this last forever? And I think that there was a few attempts at this over the millennia since that first question came up, but it really was, and I'm trying to move forward now, okay, and it really was when Einstein set down his theory about relativity that we started having the conceptual tools to make this a slightly more rigorous question, and Jim described this interaction with a few of the scientists at the time, which led to the realization that we lived in a universe that could, if you just use you develop the laws of general relativity, you could live in a universe that was collapsing in or one that was expanding out. But it was a little bit difficult to get one that would sit still, as at the time they thought it was. And of course, that was when Einstein actually introduced the cosmological constant as a way of just balancing it and making it sit still. And it was only that dozen years later that as we've heard about, the experimentalists started saying that we actually do live in a universe that is expanding. And Einstein famously called that his greatest blunder for putting the cosmological constant in. Now, of course, we now know in retrospect that it really was expanding, and that it wasn't the greatest blunder. But of course, Einstein could in fact have come up with a prediction then, and he could have been famous. So when we say the universe is expanding, let me go back to that bubble picture that Jim showed, but show a even slightly more simplified picture of the universe, because the idea that the universe is expanding is clearly a mind-boggling idea, and I think this comes back to the question that was asked a little bit earlier. And so let me show a rather simplified picture of the universe, and I am not as good at drawing those galaxies as the illustrator in that newspaper was, so I'm drawing them, each of the galaxies, as a dot. And these dots, I'm also not very good at drawing infinity, and you're supposed to imagine that these dots go on forever, to the left on the screen, to the right on the screen, into the screen, and out towards us. So you're supposed to picture us in this sea of galaxies, and the only thing that's characteristic about this particular model of the universe is that there's a typical distance between these galaxies. And so if today this is what the universe looked like, then you could say in an expanding universe, the only thing that happens is that if we wait a little while, all these distances just get a little bit larger. And so when you ask, people often find themselves asking, what is it expanding into? And you're supposed to, in this simplified picture, you're supposed to imagine that we live in this infinite sea of galaxies. It's still the same infinite sea. It's just that we've puffed a little bit of extra space between each of the galaxies and each of the points in space as time goes on. And so this is supposed to be our somewhat simple picture of what we can mean by an expanding universe. But as soon as you have that picture in mind, then you start asking all sorts of evolutionary questions. You start asking questions like, has it always been expanding like this? And is it slowing down because maybe gravity is attracting all the galaxies to each other, and that could slow that expansion down? And will this go, and could it even come to a halt someday? So that was the state of the affairs when we started doing the work that I'll be describing now. We were wondering what kind of universe did we live in, and we thought if we could look into the past to see how the universe had been expanding in the past, it would tell us a little bit more about this, and in particular might predict what would happen into the future as well, and that might tell us something about the fate of the universe. So we took advantage of something that was that the universe has to offer, which is that every now and then, in our galaxy, in all distant galaxies, one of the stars will explode, and when that star explodes, it can be tremendously bright. And I'm trying to get the film to go here. Well, yep. No, it's not triggering. Okay, so you best imagine that somewhere in this sea of stars here, one of the stars explodes. And when the movie shows, you can see that these explosions are tremendously bright. They can be brighter than the entire galaxy of stars in which that one star was found. And that means that this star can be seen at vast distances. And of course, if what we're interested in doing is learning about the past history of the expansion of the universe, then looking at vast distances is very good because we can take advantage of a simple fact that most of you will know, which is that light takes time to travel. So if you're seeing very far away, you're also seeing very far back in time. And so these supernovae allow us access to events that occurred at different times back in history. It also turns out that the supernova explosions that we started looking at, these are a subcategory called the type 1a supernova, almost always reach the same brightness and then fade away. And that means that you know how bright they are intrinsically, and therefore when you see them at different distances, you can tell how far away they are by how bright they appear to you. So it's a fairly simple rule then that you just look out, you find one of these exploding stars, you see how bright it is, it tells you how far away it is, and since you know the speed of light, you now know when did that particular explosion occur in history. So if you could find a whole series of different brightnesses of these distant supernova, they would represent different moments in history, and you could ask how much has the universe been expanding since those different moments in history. Now, in order to ask that last question, how much has it been expanding between those different moments, you take advantage of one extra trick. And that is the fact that the supernova, when it explodes, looks primarily blue. That's a short wavelength of light. But then that light travels to us in an expanding universe, and anything that's in an expanding universe that's not nailed down gets stretched exactly as the universe stretches. So by the time the light reaches us, it looks much redder, and that tells us the expansion, total expansion of the universe since that time. So to put this all together, we look into one of these distant galaxies in this picture. We see a supernova explode. It looks blue. That photon starts traveling to us, or those photons travel to us. As the universe expands, the wavelength stretches. It looks redder and redder, just as the universe stretches. And then when we read off, in the end, how much the universe has stretched in the time since that date of that explosion, which we know from the brightness. So that's the entire measurement, and I hope it feels like something that you could get behind. You know, that if you made this measurement, you would have some confidence that you would understood what the history of the expansion of the universe was. Now, this was the state of affairs when we started the project, but we did not have those supernova from distant times back in history. All we had is relatively nearby ones, representing just a few million years back. We wanted to see billions of years back in history. So we had to develop techniques to do that, and that included developing new instruments that would allow us to observe large swaths of sky on very big telescopes. So here is an example of a 4-meter telescope's 10-minute time-lapsed observation. In those 10 minutes, what you are ending up seeing in these images is all these little blue specks in the background here are the distant galaxies. You pay no attention to these foreground bright things. You're not interested in those. You want to look at these little faint specks back here. Those are galaxies that typically, in this image, those are around 4 billion light years that you're seeing back in time. And so now what you want to do is find a new speck of light of one of those stars inside one of those blue speck galaxies is going to explode. Now, of course, that's not a easy problem in of its own, but so we had to develop all sorts of computer software to take these dense fields of galaxies and point out that, for example, this one right here is brighter than it was just 3 weeks earlier. And if you subtract this image from this image, you're left with just the light of the supernova. And so with a little bit of help of the latest computers of its time, we were able to identify those supernovae that exploded in these distant galaxies. This took a number of years actually to develop this technique, and then it took a number of years to collect enough supernova with this technique to make the measurement at different points back in history. But after the end of a mere 9 years, we were ready to put on the plot of the history of the expansion of the universe, the supernova. So here's a plot, and by the way, I should apologize for the fact that this one is on a linear scale, so you're stuck worrying about what happens just before the big soup, as I call it, not the Big Bang. But on a plot like this, you can now ask, where were the supernova? Well, if the supernova that already were observed at that time are these black points here, so they're relatively nearby and so to today, which is shown in this dotted line here, and we're going to make our way backwards in time and try to see which of these decelerating lines, as we thought, we live on, so we can make a prediction as to whether it will expand forever or someday collapse. And of course, on a plot like this, you can read the brightness as telling you how far away that supernova is, and hence, because you know the speed of light, how far back in these billions of years you are. And the color, so whether it's blue or red, tells you how much the universe has stretched since that time. So that's a very simple plot to make now with these ideas in mind. And when we put the points on the plot that we found, the answer turned out to be it missed all of the lines that we expected. And so that was the surprise that we saw. And apparently we don't live in a universe that has been recently decelerating. In fact, we think that it was in the past decelerating for the first half of its life, and then the most recent half it's been accelerating. And so that, of course, was the none of the above answer to the question that we had posed. So it was not at all what we thought. This was actually going on with two different research groups at the same time. At the end, there's a bit of a race to get the final data, and so there was a surprise happening in the analyses, happening actually at two places in Berkeley. The two teams were both doing analysis, although one of them was being led from Australia. And of course, these do represent entire groups in these two teams that were all surprised by this result. All right, so this was then what led to this postulate that we live in a universe that may be dominated by some dark energy throughout all of empty space that you were just hearing about. We still do not know what that energy is, or in fact whether that really will turn out to be the answer. Perhaps we might need to actually modify Einstein's theory of general relativity instead of adding a dark energy. Now, it's hard to imagine which one's more surprising. Maybe given how well Einstein's theory of general relativity is doing, I think maybe that's the more surprising one. But having most of the universe made out of something that we've never seen before obviously is a bit of a shock. So the theorists, of course, have been very busy. And there have been a paper, I was doing the calculation, it's been one paper published trying to explain this every 24 hours since the discovery 16 years ago. And that doesn't include all the ones that are not published. The names of these theories are a pleasure to read. Some of them are hard to pronounce, like ekperiodic universe, for example. But it is, they are exploring the full range of possibilities as best we can. And I think the theorists are cheerfully willing to say that they don't stand behind their particular theory at the moment. They're really putting the ball back in our court as the experimentalists, the observers, and asking, can we tell them just a little bit more about the properties of this expansion, of this acceleration, that might help pin down what's really going on here. So this has actually been a quite active experimental area then since then. It's not the case that nobody's been doing anything about it. And that original plot that I showed you, which had some 50 supernova on it between these two teams, has now been dramatically improved. If I flip it around and turn it upside down the way the astronomers like to plot it, you'll see that we've gone from 50 to hundreds, and now the most recent one that we've just been putting together has over 1,200 supernova on the plot. And I should comment that every one of these supernova is much better measured than any of those first 50 from that original plot. So there's been dramatic progress in this measurement over these years. However, it's still fair to say that we don't know much about the properties of the dark energy as you just get a little bit further back in time. So we have some reasonable tight error bars down here, the first 5 billion years back in time, but this next 5 billion years back, this error bar is so big that you could fit anything, including things that are not dark energy, into it. And so we know very little about the properties as you watch this possibly evolve over time. And we do know that the last time there was an acceleration, if in fact the inflationary universe is true, that acceleration, the field that caused it, decayed away. And so we don't have any guarantee at all that this particular dark energy, if that's what it is, stays constant in time. We have to look for the possibilities of changes over time. So why is this so hard? Well, it turns out that measurement, although it's gotten much better, is to tell apart the different theories that could be explaining what's going on, you have to measure something that's within the thickness of that green line here that I've drawn fitting this theory. So we needed a measurement that's some 20 times more accurate than the ones we used in order to see the acceleration itself. And that's really given us a real target of a challenge to do much better. So we've been going through every one of the steps as the light comes to us from the supernova, as the supernova itself produces light, and understanding what are the sources of uncertainty and what are the sources of not only statistical error but systematic errors that could be affecting this result, because we need to bring them all a dramatic step ahead. Let me just pick on one of them, which is the one that may come to most people's mind when they're hearing about this, which is how do you know that the supernova that you're observing out there, some 5, 10 billion years back in time, behave the same as the ones you've observed nearby, so that you can be sure that when you're comparing the brightnesses, you're actually comparing the same object's brightnesses. And this meant that we've actually done a fair amount of work studying the properties of the supernova itself. And let's see, I don't know whether this movie will show, but probably not now that we didn't get the other one. So I'll just tell you that as you look at the outer atmosphere of a supernova explosion, you get a spectrum. Then the supernova expands, so the outer atmosphere in an explosion, so the outer atmosphere goes out further and becomes transparent, and you start seeing deeper and deeper and deeper and deeper into the core of the supernova explosion, and these spectra change. So it's in some sense, you can call this a CAT scan through the supernova explosion, and you can. It's very difficult to make the exact explanation of every single one of the lines, but we do recognize the different elements and the different velocities in which they're expanding, and the temperatures and states of these elements in these lines that you see, these spectral lines in the spectrum. And so the fact that you're able to match a supernova to another supernova throughout this entire CAT scan is a very compelling piece of evidence. This is something then that we've now done with a wide variety of supernova measured nearby. And so I'm showing you here a time series of different supernova that we've found with a project called the Nearby Supernova Factory, and where we actually know the relative distances of the supernova because it's relatively nearby. Now, what's a little hard to see from anywhere except maybe right next to this slide is that each of these plots shows you not one supernova with its time series, but two supernova plotted on top of each other. This one I'm showing you here is there's one supernova drawn in green and one drawn in black. This one, there's one in red and one in black, and this one in blue, one in black. And you can see that those supernova match each other so well throughout that entire CAT scan that you could actually be convinced that these are the same physics. Whereas, if you look at this feature up here on this supernova, it does not match this feature over here on this supernova, so or this pair of supernova. So you can see that you don't want to treat all the type 1As as if there's just one uniform group. You actually want to do this kind of matching of the twins, and in sets that do match, use those as your distance indicators. And that's what we are now moving towards for the next generation of the project. Today, we do not have the instrumentation to do this to very high redshift. However, tomorrow, well, in 2024 or 25, when this launches, we will. And right now, we're designing the instrumentation so that we can get those same measurements there. So I think that's all I have time for in describing the advances, and I can describe it more if you're curious in questions. But what I do want to just comment that supernova is now not alone. We do have one other technique that's actually turning out results already that are starting to match the supernova technique called Baryon acoustic oscillation. And there's a technique called weak lensing, which will also be possible to use once we get to this next generation of measurements. It has not yet made a measurement of this sort yet. So we will have several arrows in our quiver to do this work, and I think they will all be necessary since this is such a difficult measurement to make. And I'm quite optimistic that we have some shot at getting our next view of what's going on in this expansion history of the universe that might tell us which of the theories of dark energy or of gravity might be in play. Now, there's no promise that it'll work. I'm purely taking advantage of the fact that we're about to collect data at a whole new level of precision that we never had before, and the fact that cosmology still feels like something of a young field, where when you make a big step in your measurements, you often discover something. But there's nobody guarantees that we get to know the answer at this round or ever. Finally, I want to finish then with a few thoughts that I've been telling students in particular about what is it that we learn while when we do this kind of work. And the first thing I think is important to comment is that some problems are worth working on for a long time. This problem, when we originally proposed it, we said it was going to be very difficult. It was going to take us 3 years. After 3 years, we had not found our first supernova, and Jim was describing coming to visit us during those first 3 years. After we found one supernova, we still needed to find enough samples at different times back in history to make the measurement, and that took another a couple of years to develop the techniques to do this in batches, and then we had to find those batches, and so it was 10 years in that we got the answer. And I think it's important for people to remember that problems in science and problems in our world are often worth a real iterative try until you get the answer, until you get somewhere. I've been pointing out that a lot of the work was involved in trying to figure out how we were going wrong. And so that not only was that in the small, where you're just trying to figure out what's wrong with this particular measurement and what's wrong with this particular technique at the telescope, but of course it's what's wrong with our theory of cosmology, what's wrong with our theory of gravity, and that there's something so fundamental about being ready to change your mind and to learn about science, which I don't think is understood in the public well enough for them to really incorporate what science is offering them often, and it's really one of the strengths of science. And then, of course, I've been telling students, and of course most people here don't need to know this because they know it already, that science is social, and that this is work that's done with, for me, the great pleasure of conversation and time with many people, not always dressed this formally. So. Since we're just about at coffee break, I was going to just add one extra thought about all this, which is that I've been starting to ask the question, as I was just walking through these items, I've been thinking about the problem of what can we do to teach this scientific style of critical thinking to the non-scientists as well as the scientists. And so I've been playing with a few other professors and developing a course that's aimed at doing this kind of scientific style of critical thinking. And I was just going to mention that it's obvious what the motivation is. I think by now most of us, after the last few elections in different parts of the world, are finding ourselves feeling this way. Although I was starting to feel this way after several elections previous, so I feel vindicated by this current election. Not happy, but vindicated. Right? And of course, there's the basic philosophical question of, how is it that we make decisions in democratic society? Do you ask the public? Do you ask the experts? And why? And where does the authority come from? And I think in the end, much of it comes from using taking advantage of the fact that science has learned by experimentation, in some sense, over hundreds of years, a collection of heuristic tricks that we're always inventing to avoid our mental weaknesses and then play to our strengths, so that we're always actively hunting for where we're going wrong, where we're fooling ourselves, but we know very principled ways in which to deal with that, and that's what I think we should be trying to teach. And so, we've, in this particular course, for those who are curious later, I can tell you about it. We've come up with a set of concepts that we think are part of the conversation. It's a bit of the vocabulary that if you were able to teach these, and we're trying to do this very experientially, if we're able to teach these, then we think those people who've learned the course can join the conversation with the other scientists where you're looking at evidence the way we would expect to look at it. I'll just, the only one I'll point out here is number 10 here, scientific optimism and arrogance, that there's something about the training of scientists that allow us to have a certain can-do spirit that makes us be willing to take on hard problems and stick to them long enough to get a result, and I think that in itself is a bit of the training. All right, I'm going past my allotted time, so let me stop there.